In this course, we're going to have many occasions to make graphics to either plot data or model output, or to help us understand what our codes are doing when we build numerical models. And so therefore I want to start the class by showing you how to make some plots in MATLAB. And so we're going to plot a whole bunch of different types of things in this course, in this lecture. The first thing we're going to plot is a function that is defined in terms of an algebraic expression. And to make a relevant example, we're going to start off by plotting what is the univariate normal distribution. So the first example we will do, example 1, is the univariate normal distribution. And I'm going to define it algebraically right now. And we say univariate because the input will be a single variable, just x. And so it's a function of one variable, f of x. And the normal distribution is defined in terms of a Gaussian, and the Gaussian is a function that is given by the exponential of an expression which is a quadratic function or quadratic polynomial. And the particular one that's used in the normal distribution is minus x minus mu squared over 2 sigma squared, where mu and sigma are parameters. And we wanted, if it's going to be a univariate, a normal distribution, it needs to be normalized, and that means that we want the integral from minus infinity to infinity of f of x dx to be equal to 1. And if this is true, then this means that f of x is normalized. So for this to be true, there has to be a scaling factor out front to make sure the integral is equal to 1. And the particular scaling factor that's needed for this function is 1 over sigma times the square root of 2 pi. All right, so this is the first function we're going to plot. It's a function of x. It has defined in terms of two parameters, mu, which is the mean. And it's called that because it turns out that the integral from minus infinity to infinity of x f of x dx is equal to mu. And sigma is the standard deviation. And it is defined in this way. So the integral from minus infinity to infinity of x minus, well, actually it's defined in terms of where it shows up in the algebraic expression, but it turns out that if you do the following calculation, you take x and you subtract mu, you square it, multiply by f of x dx, what you get is sigma squared. So this is known as the variance. So this is the mean, and this is the variance. And so the standard deviation is the square root of the variance. The units of x are going to be equal to the units of mu, or the dimensions of x are the same as the dimensions of u, are the same as the dimensions of sigma, are the same as the dimensions of the inverse dimensions, I guess, of f of x. So you notice that here sigma is on the outside. The argument of the exponential function in this case is dimensionless. Right on the top we have x minus mu, which has the same dimensions of x or mu squared, and on the bottom we have sigma squared. So the argument of the exponential function is dimensionless, as it should be. It doesn't make sense to take the exponential of a dimensional quantity. And that means that this whole expression here, the Gaussian part, is dimensionless, and the prefactor has dimensions of inverse sigma. And so that's consistent with this. And that's consistent with this integral being unity, right? One is dimensionless. Dx has the same units as sigma, I guess, and f of x has dimensions of inverse sigma. So the whole expression is dimensionless. So we're going to plot this function first in MATLAB, and I'm going to show you what it looks like. This here is the plot we're going to make. For this particular example, mu is equal to 10, right, which tells us where the shape, the bell shape is located. If I change mu, the shape doesn't change, but the location of the function will change. So if I pick mu to be 15, then these three curves will be shifted over to 15, and the width and so on will be the same. And there's three normal distributions plotted here, one for sigma equals to 1, one for sigma equals to 2, and one for sigma equals to 3. And you could see that the bigger sigma is, the broader and wider is the distribution, and the smaller sigma is, the narrower and taller it is. Right, there's this inverse relationship because the area has to integrate to 1. So if you make sigma small, the distribution is narrower, but it has to be taller to fit the same unit amount of area. And the converse is true, where sigma is very wide, the function f, the function f has to be shorter everywhere for the area to be 1 under the curve. And you notice that as x goes to infinity or minus infinity, in other words, when we move far away from mu, the function goes to 0. And that's clear from here, right? If x is far from mu, then the part in the numerator here will be very big. And since we have e to a very big number, the whole exponential thing will go to 0. And that's consistent with the graph we just looked at. All right, so that's the first example. I think we should go to MATLAB and plot it before we go any further. All right, so welcome back. So we're going to making plots in MATLAB, and we're going to plot the univariate normal distribution, the bell-shaped curve. And over here, I have the notes from the lecture, and my text editor is down here, and the MATLAB session is running over here in a terminal. And so we're going to build up the normal distribution bit by bit using what is called an inline function. And that's defined in the following way. So f is equal to, and use this little at symbol, x means that f is going to be a function of x. And the way we're going to define it, well, here we're just going to have f of x return x. So if I run this script, ex1, by just typing its name at the prompt, it tells me that I have a defined variable f, and it's a function handle with a value of, just returns x. So if I do f of 4, for example, it returns 4, f of minus 9 returns 9. All right, so it just returns x, so that's a little bit boring. Now we're going to have it return the mean, or x minus the mean. So we're going to build up this argument of the exponential bit by bit so you can see how the plotting works. So I'm going to subtract mu. Oh, sorry. Now x is going to be a function of mu also, which is a parameter, minus mu. And then I now have to define a bunch of x values at which I'm going to evaluate my function. So I'm going to pick a spacing dx to be 1 e to the minus 3. So 10 to the minus 3 is the spacing, and x will start at 0 and go in steps of dx all the way up to 20. All right, so let me run this ex1, and if I type whose, it will tell me the variables defined so far. I have y. Oh, I need to have y. Why do I have y? Hold on, clear all. ex1, whose. Right, so I have three variables, x, f, and dx. These three variables. Dx is just a scalar, just a number, but x is a whole range of numbers. So it's a whole list of numbers, or a vector of numbers from 0 to 20 in steps of 10 to the minus 3. So the length of it, and do the length of x, is 20,001 in this case. And I can then evaluate the function f at all those x values and make a plot. So if I plot x versus f of x, and I pick a value for mu, so I'm going to pick 10 as the example I had before, I get the following. So let me add some, it's hard to see, so I'll make the plot a little bit nicer. So I'm going to plot x, f of x and 10, like this, and then I'm going to make the font size bigger so you can see. So set, and there's a key variable after you make a plot called get current axis GCA, and it has properties. So if I do get GCA, I can see all the properties that can be modified to make the plot prettier. So one of them is font size, and I'm going to make that 16. And another one is the line width, which is a little bit thin. So set GCA line. Yeah, sorry, that's not. I have to get a handle for the plot, and then I could set that. Set H line width 2. So let's run that. EX1. So now I have a thick line and bigger numbers. I guess some other things I could do to make it nicer is add an X label and a Y label. So X label is X and Y label is f of X. And I'm going to add a grid. So grid lines, grid on. And let's run it again. So now I have labels X and f of X. I have the grids, and I'm plotting X minus 10 in this case. I could do a hold on. Let me see here. Let me move this up here like this, and plot this once, and plot this twice, and then do a hold on in between the plots. So normally MATLAB will overwrite the previous plot unless you tell it to keep the current plot, and it'll plot on top of it. And so I can, if I run it now, I should have well, it plotted twice. I guess one thing I can do is then pick a different mean. So if I pick this to be 5, for example, and I'll give them color. So the first one will be black, and the second one will be red. So the little K and the R, these are these are codes to tell MATLAB to use black for the first line and red for the second line. X1. Let me clear the figure. So I should do that, I guess, before I start. Figure 1, CLF. EX1, I run it again. And now I have the 2 lines. So the red one, which is the second one, has mu equals to 5, so it crosses the 0 at 5. The second one is equal to 0 at the value of 10. Alright, so let's now further modify our function. So this time I just plot a straight line. Now I'm going to square it. Right, the goal is to slowly construct the argument of this function. So if I square it, then we should get parabolas, right? So let's try it. So I get 2 parabolas. The minimum is at 0. The minimum is 0, right? I'm plotting a squared quantity, which is always positive. It's going to be 0 when x is mu. So for the red one, it's 0 at 5. For the second one, it's 0 at 10. All right, so we get these parabolas. Now I'm going to flip the sign, like here. So I'll put a minus and run it again. EX1. Now they're the same, but they're parabolas that are pointing downwards. The curvature is negative because I have a maximum. And now we're going to add the 2 sigma squared scaling. So I need to include a new parameter in my function, sig, and then I will divide this by 2 times sig squared. And then when I call it, I need to pass it 3 arguments, the x values, the mean, and the sigma. So I'll put sigma equals to 1 and sigma equals to 2. And let's run it again. And the sigma of 2, it's much broader, right? So you have this, because you're dividing by 2, so it's not decreasing as fast. And then I guess the next thing is to exponentiate this to make the Gaussians. So let's do that. exp, like this. And let's run it again. EX1. So now I get these bell-shaped curves. I guess I could extend the range a little bit. The red one is going off the page a little bit. So let me, well, maybe I'm going to flip these around instead. Let me do that. Well, no, I'll make it go off the page. So I'll start at minus 10 instead. Minus 10 up to 20. So let's run it again. Right, so now this is the one with the mean of 5 and standard deviation of 2. It's a little bit broader, and the other one is narrower. So you see now the area under the 2 curves is not the same, and that's because I haven't added the prefactor the normalization. So we should have this next. So now let's make sure they integrate to 1. So I will divide by sigma times the square root of 2 times pi. And now they should be properly normalized. So let's run it again. EX1. So the area under these two curves is supposed to be equal to each other. Let's add a third one plot. So we have 1, 2, and a third one. And we'll make the next one a mean of 0 and a width of 3, let's say. And I'll make the color green. Let's try it again. So now I have 3 Gaussians. It's very similar to the one that I showed you before, except now the location parameters are different. The very broad one has a location parameter of 0, a mean of 0. This one has a mean of 5, the intermediate one, and the last one has a mean of 10. Whereas in the one I showed before, it always had the mean of 10. So maybe we can check these integrals, right? It's supposed to be that the integral of f of x is 1, and the mean, this x times f of x, should be mu, and this square deviation from the mean has supposed to give us sigma squared if I integrate that. So to do the integrals numerically, I can do it in the following way. If this is the axis here, like this, and this is y, and I have a function, right? I can divide up the x into these discrete intervals, and I can compute or estimate the area by just calculating the height of, or the area of all these little rectangles like this, right? So the height of these rectangles is going to be given roughly by f at xi, where this here, the center would be xi, or maybe the endpoint, and the width is going to be delta x. So if I define a bunch of point xi is equal to 0, delta x, hold on, like this, x not equals 0, x1 is equal to delta x, x2 is equal to 2 delta x, and so on, all the way up to xn is equal to n delta x. And at each point I evaluate the function f of x0, which is f of 0, f of delta x, which is f of delta x, f of x2, which is f of 2 delta x, and so on, all the way up to f of xn, which is equal to f of n delta x. And then if I multiply all of these by, this is the height of all these rectangles, right? And I multiply by dx, and I sum. So if I sum for I equals 1 to n delta x times f of xi, then I'm going to be adding the area of a bunch of little rectangles. And this should be a good approximation to the integral from minus infinity to infinity of f of x dx. That's true provided that my range is wide enough so that the function goes to 0 at the endpoints. And that's pretty true for all these 3 examples. By the time I reach the interval at minus 10 and at 20, all the function is pretty much equal to 0. So that integral, so the argument of the integrand of the integral should vanish. And this should be a good approximation. Otherwise, I'd have to make the limits even farther out to make sure that's true. So it's close to it's close to minus infinity to infinity, even though I don't start x naught at minus infinity and n at infinity. That's because by the time we're at n delta x, f is already 0. All right, let's try that in MATLAB down here. So I'm going to sum f of the first one, x, 10, and 1 times dx. That's supposed to be 1. Sum of the second one, f, x, 5, and 2 star dx should be also 1. And sum of f of x, 0, 3 times dx should also be 1. If they're all 3 are normalized, these 3 sums should all give me 1. So let's try it. So I get 1, 1, and 0.996 for the last one. That's the width of 3. And you notice that out here, it's still maybe not quite extends far enough. So maybe I should extend the range a little bit further. Let's go to minus 15 and try again. EX1. Right, and now they're pretty close to all being 1. So that's, I checked the normalization condition for all 3. So it's not a proof, but it's simply showing that, all right, I normalized it correctly. Now let's try to compute the means for all 3. So that's pretty straightforward. I just multiply by x. And the little dot here means multiply component by component. So multiply the first number inside the long list of x with the first output of f of x, the second with the second, and then sum. X dot star, x dot star. So the integrals should give me 10, 5, and 0. Let's try it. So what do we get? 10, 5, and 4.45 times 10 to the minus 6, which is pretty close to 0, so that's not too bad. All right, so for the next one, I subtract the mean minus, in this case, the first one, the mean is 10, right? That's what I got, 10. And I have 10, and I square. Oops, I square. And then I multiply by f of x. This one, the mean is 5, so I subtract 5. And I square and multiply. And the last one, I subtract 0. So we'll just square like that. So now the first integral should give me 1, because 1 squared is 1. The second one should give me 4, because the standard deviation 2 squared is 4. And the last one should give us 9. So let's try it. And what we get is 1, 4, and 8.999 is pretty close to 9. So it seems that these 3 integrals, the normalization, the mean, and the variance, they all work out to what they should be by simply approximating the integral using this these little rectangles. Okay, so that's the standard deviation. Let's review quickly. The standard deviation, or sorry, not the standard, the normal distribution can be defined also for multivariate where you have many inputs, but so far we've looked at only the univariate case. It has a bell shape. There's this prefactor in front that normalizes it, and it is equal to 1 over sigma times root 2 pi, which gives the dimensions of f of x to be those of the inverse of those of sigma, or the inverse of those of x. So f of x is what's known as a probability density function. So it has the amount of probability per unit x interval. Mu is the mean, and sigma is the standard deviation. And it has this nice characteristic bell shape. All right, so we'll see this function very often because it shows up in error analysis all the time.